Okay, in this section, we're going to use our knowledge of SOHCAHTOA to solve right triangles. So what does it mean to solve a right triangle? Well, it means to, one way or another, determine the measures of all three of its sides and all three of its angles. So a triangle is solved when you know all of its lengths and angles. Okay, and to do this, I'm going to introduce a labeling convention. So for a triangle, we label the vertices using capital letters, and we label the side lengths using lowercase letters. Moreover, the letter for the side length is always the lowercase version of its opposite vertex. So because angle A is here, side A is opposite, which means we must put side B down here with a lowercase b, and side C, opposite angle C, with a lowercase c. And we would use the vertices in the label for the triangle itself, call this triangle ABC. Okay, so let's get into solving some triangles. All right, in this example, we're given some information about a triangle, but not everything. We have one side length, the lowercase a, and two angles, capital B and capital C. And we don't even have a picture of this triangle. And truth be told, you don't actually need to draw a picture of the triangle to solve it if you just understand how all the A, B's, and C's are related to each other. But let's try and draw this triangle because I think it's going to help. So angle C is 90 degrees. Let's put that right here. And side A is 25.3 centimeters. Let's decree that that's side A right there. And we'll put angle B at the top. And angle B is 28 degrees 45 minutes. So that's about 30 degrees. We know what a 30-degree angle is approximately like. So there's our angle B. And that's exactly what was given in the information, nothing else about the triangle. But you can imagine that this triangle is completely determined by that given information. Right? We have no choice but to complete the triangle by extending side C this way and side B this way. So this is side little b, opposite capital B, and this is side little c, opposite capital C, and this will be vertex or angle A, which is opposite little a. And we can even put in the given information. We know this is 28 degrees and 45 minutes, and we already have our 90 degrees marked for C. Okay, so let's write down a template for our final answer. The triangle will be solved when all 6 measures have information in them. But we already know some of it, like C was given to be 90 degrees, capital B was given to be 28 degrees and 45 minutes, and little a was given as 25.3 centimeters. So our plan here is to use everything we understand about triangles, relying heavily on right triangle trigonometry, that is SOHCAHTOA, to determine all the missing measures from this triangle. Okay, it looks like the first thing we can get that's very easy is capital A, because you're never going to be stuck with 2 out of 3 angles from a triangle. You can always find the third one by using the fact that 3 angles in a triangle add up to 180 degrees. So let's get capital A. We know that A plus B plus C is 180 degrees. And so we can subtract B and C from 180 degrees. All right, so 180 minus 90 is 90, so this is like 90 minus 28.45. Well, let's write 90 degrees as 89 degrees and 60 minutes. So the subtraction gives us 15 there and 61. So capital A is 61 degrees 15 minutes. All right, well, all we have to do is figure out side B and side C. We're going to use trigonometry for that. So let's start by finding side B. Now what we need to do is relate it to one of the known sides and one of the known angles. Well, you might notice that if we work with angle B, side A is adjacent to that, and side B, which is unknown, is the opposite. So we could say something like this. Tangent of B is little b, opposite of it, divided by little a, which is adjacent to it, since tangent is opposite over adjacent. And therefore, solving for little b, which is what we're after, we can say little b is a times tangent of capital B. And we have both of those pieces of information. Little a is 25.3 centimeters, and capital B was given as 28 degrees, 45 minutes. So using a calculator, I get that little b is 13.8800553, that goes on forever, centimeters. Okay, so going to our final answer up here, let's round little b using the significant figures given in the problem. So we can see to conform with the measurement A, we should round 13.88 to 13.9 centimeters. All right, so we just have to find little c. Now, before we do that, there are a few important points that need to be made right now. Okay, one of them was, going back to how we could find little b, using the tangent of capital B isn't the only way we could have done it. We could have found little b by noting that tangent of capital A was little a over little b, and thus solving for b that way. And ostensibly, there's nothing wrong with that method because we know what capital A is. We worked it out. The problem is that what if we'd made a mistake calculating our capital A? Now we're reusing that figure in a further calculation, which would propagate any mistake that we might have made calculating capital A. Notice that by using capital B and little a, we were appealing directly to the given information. So as a matter of principle, all things being equal, try and appeal directly to the given information. That way, if you make a mistake, you're keeping that mistake isolated to just one small part of the problem and not letting that mistake bleed into other areas of the problem. And the other important thing to mention is that we wrote the rounded version of little b here, 13.9 centimeters, because we are presenting this as our final answer. And our final answer must have units, and it must have the correct level of precision, which should match the precision of the given information. However, if we were going to need b in a further calculation, we should not use 13.9. We should use the 13.8800553 that's down here. And this is because we only round as our final answer. We never round partway through a problem and then use a rounded figure to calculate. Okay, now let's find little c. So let's appeal to our triangle here. And we have a number of different ways we could relate all the sides. For one thing, this is a right triangle, so you could use the Pythagorean theorem to find little c. But that would involve hoping that you calculated b correctly and appealing to all the digits of little b. But notice if we just use little a and angle b and whatever trig function relates them to side c, then we're appealing directly to the given information. It looks like cosine of capital B is adjacent a over hypotenuse c. So let's use that. So we know cosine of capital B is side a over side c. And we're now just going to solve for little c. So bringing it over here, we have c times cosine of b is equal to a. And therefore, little c is a divided by cosine of b. And little a was given as 25.3 centimeters. And cosine of b would be cosine of 28 degrees, 45 minutes. Okay, so on my calculator, I got 28.85733 763, blah, blah, blah. That's centimeters. But we know to round that to 28.9 for our final answer. Well, let's go put that in. Okay, we have all 6 measures of the triangle, so the triangle is solved. Okay, final comment is that we didn't have to draw an accurate triangle. I said at the beginning of this problem that you don't have to draw a triangle at all, although it is helpful. But we could have drawn a terrible triangle. Let's draw a terrible triangle. Worst triangle ever. All we have to do is make sure that the side lengths and vertices are labeled appropriately relative to each other, so that the A is opposite A, B is opposite B, and C is opposite C. And as long as you understand, like say just calling this guy 2845, and as long as you understand the SOHCAHTOA, then you're able to put all the lengths together using trig functions and determine all the other lengths, and your calculator will do the work. So while I do think it's a good idea to try and practice interpreting the triangle correctly, I wouldn't sweat it though. Okay, here we have another triangle in need of solving. So let's try to draw it. We've got angle C, which is 90 degrees. And this time we're given 2 sides and no other angles. So we can say side A right here is 44.3 centimeters. And let's call side B over here, which is 55.9 centimeters. So that's what's given, and you can probably imagine that there's only one way to complete this triangle, which would be, of course, connecting these 2 opposite vertices. All right, so we need to determine capital A, capital B, and little c. Let's write down a template for our final answer. Okay, well last time we had 2 out of the 3 angles given, so we were able to find that last angle by just knowing that they add up to 180 degrees. That's not going to work this time when you only have 1 out of the 3 angles. So what we're going to have to do is use an inverse trig function to find one of the missing angles. So let's look at what's given and one of the angles we're interested in and see what we can figure out. Well, it looks like tangent of A is little a divided by little b, and we're given all of that, so we can use that to figure out what capital A is. So tangent of capital A is little a over little b, that's opposite over adjacent, and therefore angle A is the inverse tangent of little a over little b. So that would be 44.3 centimeters divided by 55.9 centimeters. So using a calculator, I got 38.3963524, etc. degrees. Okay, let's round that to the nearest degree for our final answer. So we'll go 38 degrees. And now we're going to find capital B. But now we do have 2 out of the 3 angles, so we can use the 180 degrees trick. We know that capital B is 180 degrees minus capital A minus capital C, which is 90. So 180 degrees minus 90 degrees is 90. So capital B is 90 degrees minus A. Now on our calculator, we do not want to use the rounded figure 38 degrees. We want to use the very precise figure 38.396 blah blah blah. So that's the most recent figure in the calculator, so we can just go 90 minus and then use the answer button on the calculator to get 51.6036476 degrees. Okay, and that rounds to 52 degrees. So it just remains to find little c. Well, we could use the fact that we know that sine of capital A is little a divided by little c. However, if we do that, we need to use, of course, the precise version of capital A in our calculation. However, since this is a right triangle and we're given little a and we're given little b, we might as well just use the Pythagorean theorem to find little c. By the Pythagorean theorem, c squared is a squared plus b squared. So on a calculator, I got that c squared is 5,087.3 square centimeters. And therefore, taking the square root, we get 71.32531108, etc. centimeters. Let's go put that in our final answer. So we need to round to the precision that's given in the problem here. So that would be 71.3. And we need the units, centimeters. And that's our final answer. You may have noticed that I actually incorporate the units directly in the formulas that I'm calculating. You don't actually have to do that. I just do that to make sure all the dimensions work out the way I expect. You do need units wherever you're presenting your final answer. So I absolutely recommend that with a problem like this, you set up a little space for capital A, capital B, capital C, lowercase a, lowercase b, and lowercase c, and you put the final answer there with the correct rounding and the correct units. All right, the remaining set of examples are actual word problems representing actual physical situations. In order to get into those, we do need to make a couple of definitions, and those are an angle of elevation and an angle of depression. So suppose you have a point of reference, like say the edge of a cliff or something. You can imagine a horizontal, even if it doesn't physically exist, coming straight out from the point of reference. An angle of elevation is always read upward from the horizontal. So let's say here's your point of reference and you're tracking, say, a plane flying in the sky. You could describe the angle of elevation to that plane using this angle right here. You could also describe, say, a point on the ground below you. Let's say there's a tree or something, and you're trying to describe the angle down to the base of that tree. You would use something called an angle of depression for that. So the key is that angles of elevation and angles of depression are always read from the horizontal. Okay, let's see some examples. All right, so here we're interested in learning the height of this tree. And we don't want to cut the tree down to measure it or climb it to measure it. So we're going to use trigonometry, where we can certainly measure a distance along the ground, as we did here, and we can measure an angle from a certain distance away up to the top of the tree. We have an angle of elevation of 60.4 degrees. And you can see it's an angle of elevation because it reads upward from the horizontal. So question is find h, right? The height of the tree. Well, the way to approach this is simply to figure out which trig function is relevant relating h and the given length that we have and the given angle that we have. So we only need one of either sine, cosine, or tangent to answer this question. And you can probably see, using SOHCAHTOA, that tangent is the function we need because it will relate the opposite to the adjacent, and those are the sides that we're talking about. So we know that tangent of 60.4 degrees is equal to the opposite side, which is h, divided by 15.5 meters. So solving this equation for h, we get that h is 15.5 meters times tangent of 60.4 degrees. So it's just a matter of doing the calculation on a calculator now. On my calculator, I got 27.28493,436 meters. Okay, well that's far too precise for this problem. We have no choice but to round our answer to the precision given in the problem, which would be the nearest tenth of a meter. So we'll just say 27.3 meters. And again, if we were going to use this h in a further calculation, we would need to use the very precise one that we calculated, but in our final answer, we have to use the rounded version. If we wanted to get more precise, we would just have to be more precise with this measurement we took down here. Now we can answer that age-old question. Just use trigonometry. All right, in this situation, we have two buildings with a 42-foot street between them. So let's draw that. And we're interested in the angle of depression from the top of a 97-foot building. Okay, let's call this guy 97 feet. And let's say that's our reference point. So the angle of depression is from the top of this 97-foot building to the base of the building across the street. So here's the base of the building across the street. And we know that the street here is 42 feet. And the angle of depression must be always read from the horizontal downwards. So we have an imaginary horizontal here. So this is the angle of depression that we're after. We'll call it theta. Okay. Now let's move the 97 feet measure a little closer to things. This is 97 feet. And you can see we have a right triangle. Now, unfortunately, the theta that we're interested in is not part of this right triangle. However, we have two really good options. One is that you could determine that angle there, because that angle is indeed part of the right triangle. And once you find that angle, you'll notice that theta is just the complement of it. So we could do all the trig we needed to figure out this angle. Let's call it alpha. And then theta is just 90 degrees minus alpha, and we're done. But there's even a better way, and that's noting that angle theta is congruent to the angle right down there. We can call that one theta too. Okay, this is just a fact from geometry. If you have two parallel lines and a transversal, that alternate interior angles are going to be congruent, and that's what we have here. So we can just find this theta, and that'll be our answer. Okay, so we just have to think of which trig function relates theta that we're interested in here with the two given sides. And of course, you can probably guess that's tangent. Incidentally, another reason I write these units in is so you can see that the units in this case cancel, and we get a pure ratio. Trigonometric functions always produce a pure unitless ratio. So what we're after is theta, which we know will be the inverse tangent of 97 over 42. Okay, calculator time. I get 66.58788,583 degrees. Let's round that to the nearest degree. So that would be 67 degrees. So we can say the angle of depression is 67 degrees. So that seemed like vital information we couldn't go through life without knowing. Okay, here we have a diagram with some measures given, and we want to find h, which is this entire length here on the right side. So we're going to need a plan. Well, what are we given? We're given 50 feet is this length, which is actually the same as this length over here, so we have part of h. I recommend pausing the video right now and actually legitimately trying to come up with a plan on your own here. And then when you're ready, hit unpause. All right, so we have two triangles here, and we're going to need to use both of them. So we know something about this triangle. We know that this length is 50 feet. Now notice that 50 feet is the opposite side to 22 degrees, which means we could use the tangent function to find the adjacent side to 22 degrees, which is this side right here. Okay, well, now that we know that side, which is shared in the triangle above, we can now use the tangent function to find the opposite side of 51 degrees, using the adjacent side that we worked out a minute ago. Now, once we have this opposite side of 51 degrees, well, h is just that plus 50. So we're done. So that's our plan. So let's call this intermediate length x, and our first job will be to find x. And we're going to use the smaller triangle. Let's call it the lower triangle. So we're going to note that tangent of 22 degrees is 50 feet divided by x. So moving the x to the left and dividing by tangent, we get x is 50 feet divided by tangent of 22 degrees. So on the calculator, I get x is 123.7543427. And that's feet. Remember, tangent of 22 is a pure unitless ratio, so it doesn't contribute a unit. All right. Now we have our x. We can consult the upper triangle to find this length right here. Why don't we call that y? So we know. So we're going to find y, and we're going to use the upper triangle. Well, we know that tangent of 51 degrees is y over x. So solving for y would just mean moving x to the other side. So we have y is equal to x times tangent of 51 degrees. Well, remember, x is 123.7543427, and we cannot round that yet, not until we're presenting a final answer. But the good news is that number is the most recent thing in our calculator. So if you just hit multiply, it'll automatically load that answer in. Multiply by tangent of 51, and we get that y is 152.8238859 feet. Okay, well, isn't h just 50 feet plus that? Okay, so the very precise version of h would be 202.82 blah, 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 blah feet. However, we need to round our answer to the precision given in the problem statement. It looks like we used tenth of a feet, so let's round our h to tenth of a foot. And there we are. All right, this is a neat one. Let's find the diameter of the sun. So, okay, let's draw the sun. Let's assume that the Earth is just a point, and I'm going to exaggerate the relative sizes and distances here so that we can actually see the triangle that's formed. Now, there's a tool called a transit that measures the angle of something. For instance, if you're staring at the sun, which is generally not a safe thing to do, you can use a transit to measure an angle by holding it up and putting the two ends of the transit on the thing that you're measuring, and then it'll tell you what the angle is in between. So if we did that to the sun, we would get 32 minutes of angle. That's about half of a degree. And we want to know the diameter of the sun, which is this length right here. Okay. Well, in order to do this, we're going to need to build a right triangle. So why don't we just cut this in half? And that cuts our angle in half here to actually 16 arc minutes, which would be about 1/4 of a degree. And you can see we now have a right triangle. We can use trigonometry. But we're going to need at least one of the side lengths on here. So namely, we're going to need this side length right here, which is the distance from the Earth to the sun.
How far away is the sun?
93 million miles.
Correct. That is 93 million miles. Okay, so our plan is we're going to use SOHCAHTOA, namely the tangent function, to find this length right here, which is the radius of the sun, and then we'll double it to get our diameter. So let's call this length here little r. And we can see that tangent of 16 minutes is little r divided by 93 million miles. Well then therefore r is 93 million miles times the tangent of 16 minutes. Okay, let's do this calculation. Now remember, we're not putting in 16 for the tangent, we're putting in 16 over 60 to convert to degrees. So on a calculator, I get 432,844.7799 miles. Okay, the diameter will be twice the radius. So we'll just say that d is 2 times that. And we get 865,689.5598. But that's way too precise for the measurements that were given, so we should round this to 2 significant figures. So we'll just say that the diameter of the sun is 870,000 miles.
And the diameter of the sun is 870,000 miles.
Yeah, I just said that.